Okay, let's take a look and see what we did in class today. So let's go share screen, share screen, share screen. Okay, so here's what we did today. We did this idea of something called implicit differentiation. It basically follows the same logic of what we do when we differentiate, but I'm just going to kind of add a step just to show you what I'm doing. So from before, when we take the derivative of x cubed with respect to x, and that's usually how we're reading that, the derivative of our function x cubed with respect to x. So you all know by the power rule, that's 3x squared. Really what it is it's 3x squared dx, because we're taking the derivative of this x with respect to x. But when you have the same thing in the numerator and the denominator, you end up with crossing them off. That's why we just said it was 3x squared. So doing this derivative over here, we're going to use the power rule followed by the chain rule. So this is going to be 3 times x squared minus 5 squared. And then the chain rule says take the derivative of what's inside. So 2x, that derivative. And technically, again, it's dx. But since we have dx in the numerator and the denominator, crosses off. So really, I mean, this guy is just 3x squared, like I said, and this one right here is 3 times quantity x squared minus 5 squared times 2x. Okay. That's what we did. Now I want to show you what we can do here. We can actually take the derivative of y with respect to x, and we're going to follow the same rule. It's just like the one above. We're going to say that this is 3y squared. But now here's the thing. We need to multiply that by, instead of dx, we're taking the derivative of y with respect to x. So this right here is my whole derivative. To figure out the derivative of y cubed, what I need to do is I need to say it's going to be 3y squared times the derivative of y with respect to x. So this is kind of our jumping off point. Now, to work through an actual implicit differentiation problem, you're going to differentiate both sides of an equation with respect to x or whatever variable I ask. If a term includes a y, then we're going to multiply it by dy dx. We're going to collect all the dy dx terms on the left side. We're going to get everything else on the right side. We're going to factor out the dy dx, and we're going to solve our equations. Let me kind of walk you through this logic. So x squared plus 3x minus y squared. So we're going to take the derivative of each part. So it's 2x dx. But again, the dx's just go away. Plus 3, the derivative of 3x is 3 dx, which again, the dx's just go away. Minus the derivative of y squared is 2y dy dx, equals the derivative of 20, which is a constant, is 0. So now what we really have is we have 2x plus 3 minus 2y dy dx equals 0. We need to gather all the dy dx's on one side. We need to gather the non-dy dx's on the other. So what I'm actually going to do is I'm going to do this. I'm going to add 2y dy dx to both sides. 2y dy dx. And what I'm going to end up with is I'm going to end up with 2x plus 3 equals 2y dy dx. Or just kind of flip it around. 2y dy dx equals 2x plus 3. And now what I'm going to do is I'm going to divide both sides by 2y, 2y, 2y. And I'm going to find out in this case that dy dx is going to be a function in terms of y's and x's. It's going to be 2x plus 3 over 2y. And that would be my derivative. And again, the same logic kind of follows through on every one. So let me walk through this one. Y equals 3x squared plus xy. So I'm going to take the derivative of the left side, which is y, and the derivative of y is 1. But it's 1 dy dx because I'm taking the derivative with respect to x, equals derivative of 3x squared is 6x dx. But again, those cancel out, become 1. Now, the thing to be careful about over here is technically I got a product rule going on. I've got u is x, I got v is y. So u prime is going to be that 1 dx, but again, I don't need to worry about the dx. Is the v prime is going to be 1 dy dx. And if you remember, the product rule is u v prime plus u prime v. So in order to take this derivative here, I take u, which is x. I take v prime, which is dy dx, plus u prime, which is 1, and v, which is y, so plus 1y. And now what I'm going to do is I'm going to gather the dy's dx's on one side and the non-dy dx's on the other. So I'm going to do minus x dy dx, minus x dy dx. And this becomes 1 dy dx minus x dy dx equals 6x plus y. I'm going to factor the dy dx out. Dy dx is out. Becomes 1 minus x equals 6x plus y. And then I'm going to divide both sides by 1 minus x to get the dy dx by itself. So I find out that dy dx equals 6x plus y over 1 minus x. So again, this is how we do implicit differentiation. We're always going to follow that dy dx part, or whatever is asked for. Okay, so the other two I'll leave to check the notes online, and you can actually get those answers. So now what I'm going to do is work on the backside. Pardon the cough. So what I'm going to do is I'm going to take the derivative of this guy. And this guy right here, x squared plus y squared equals 4. So for dy dx, I take my first derivative, x squared. The derivative of that is 2x. Dx cancels out. Plus the derivative of y squared is 2y. Dy dx is going to equal the derivative of 4, which is 0. Let's get the non-dy dx's on one side. So I'm going to do minus 2x from both sides. I'm going to find that 2y dy dx equals negative 2x. Divide both sides by 2y. And what I'm going to find out is that dy dx is going to equal, those 2's cancel out, negative x over y. So that's my derivative of my function. And if you know what that function is actually a circle. Let me kind of walk through the idea of what this guy looks like. So 1, 2, 1, 2, 1, 2, 1, 2. So really what it is a circle centered at the origin with a radius of 2. So it really kind of looks like this. Now what we want to do is we want to find out where the derivative is positive, where the derivative is negative, where the derivative is 0, where the derivative is undefined. So if you think about what does a positive derivative look like? Well, positive derivative is a positive slope line. So you're kind of looking at something that looks like this. If you look at your circle, where do we see our positive slope lines? Well, I see one right here. So one of them is going to be in quadrant 2. The other one I see is going to be right down here. That's going to be in quadrant 4. And if you think about what you got going on in each one of these, quadrant 2 has negative x's and has positive y values. That's quadrant 1 if we look at that. So our x's are negative, our y's are positive. And if you look at our formula for derivative says we take our x values. So we said that our x values are negative in quadrant 3. We take our y's are positive in quadrant 3. A negative over a positive gives you a negative, but we also have that negative sign out front. So that gives me my positive. That's why we're positive in quadrant 2. Same idea holds for quadrant 4, where you have positive x's and negative y's. So this ends up with a positive over a negative, which gives us a negative. But that negative sign that's with the xy makes it a positive. That's why we're positive in 2 and 3, which if you look at a circle, you're positive in quadrants 2 and 4, not 3, 2 and 4. Now we're going to look at our negative ones. And again, our negative slopes are going to look like that. Where we have negative slopes for derivatives are going to be right here in quadrant 1 and in quadrant 3. And you can follow, again, the same logic that when I'm in quadrant 1, I have positive numbers for x and positive numbers for y. That gives me an overall positive. But when I multiply times this negative, Gonna give me a negative value. There's my negative slope, and the same for quadrant 3. In quadrant 3, I'm gonna have negative over negative, which gives me positive. And then a positive times a negative gives me a negative. So again, just kind of a visualization of what we just did with this rule. If we think about slopes of 0, 0 slopes are horizontal lines. And if you think about where we have our horizontal lines, we have a horizontal line right here, and we have a horizontal line right there. And what we're going to find out is that it's 0 everywhere on the y-axis. And if you really want to know why, because again, my x values here are 0. My y values are either positive or they're negative. So positive up here and negative down here. If I got a 0 in the numerator, that gives me a 0 slope. So that tells me my slope is 0 there. Last but not least, where am I undefined? Undefined are vertical lines. I got a vertical line here, 1. I got a vertical line here, 2. So what that tells me is the x-axis is where I'm undefined, because that's where in the circle we got our vertical tangents. So that's the idea of working with the derivative. And my last piece is, like I said, I can take derivative with respect to anything. So I want to take the derivative of a with respect to t. So I'm actually taking the derivative with respect to t. So when I do this problem, the derivative of a, that's a variable. So that gives me a 1 times the derivative of a with respect to t. Take the derivative of the other side, pi r squared. Pi is a constant, so this actually becomes 2 pi r times dr dt, because r is my variable. So basically that tells me that the derivative of the area of my function is equal to 2 pi r dr dt, which is basically the circumference. So to figure out the area of a circle, you can actually use the derivative, which is the circumference of your circle. And last but not least, this one, derivative of v with respect to t. So derivative of volume with respect to time, because it's 1 times dv dt, derivative of v, equals 3s squared times ds dt. So our derivative of volume with respect to time is equal to 3 times r side squared times ds dt. And that's what we did in class today. I asked you to take a look at the homework. There's front and back. I just asked people to work on the first 4 questions. And please come to class with any questions you may have. Other than that, hopefully that helps. And I'll see you all next class.